Hello.
Yes, sir.
Somebody, Siddharth Shah is listening to some other lecture.
No, no, sir. It wasn't me.
Yeah. Who is it? Somebody, what is it? Some oxidation?
Sir, it was Misakar. Actually, my mom is teaching to
Okay.
students, to her students.
Okay, okay. All right.
I was on mute mode.
Okay. All right. Um, uh, so, yeah, let's quickly recollect what was done in the. So I asked you to read data mutation, no? Data mutation. Hello.
Yes, sir.
Yes, sir.
Can somebody comprise?
Yes, sir.
Yes,
Who is
sir.
good?
In the
In
lecture,
the lecture,
they are
they
talking
are
about
talking
one of
about
the
one of the
mutators. And in the starting slides, they were talking about how we can use the data abstraction mutator on the primitive data, then on the compound data, and on pair, on list pair data structure, pair. How we can do mutation on pair also. After that, they move on to the stack data structure. So means how can we do the we can implement a stack, but in that implementation there was a some limitations because we have not isolated the stack. So another alternative way to do this is they use defensive programming. In that means in the previous lecture we have seen about tag data and all. So they use that strategy. And moving on, they also talk about queue data structure. And in queue data structure they did the implementation, and at the end they were talking about running time complexity there, about that. And
Yeah, wait. Let me ask questions. So there are three operations which we see for new in this thing. One was set bang, the other is set char bang, and set color bang. Yeah. Hello. Can you hear me?
yes.
Yes. So what is set bang for?
So you are talking about lecture, means the you asked us to watch the lecture 12 or previous lecture.
Or which one?
Actually, I was talking about the lecture 12 you asked us to watch.
Lecture 12, no? Let me see.
Yes, sir.
Let me see what is lecture 12. 1 second.
I was giving the summary of lecture 12.
Yeah, we are talking about in lecture 12 also it's there, no? Set bang, and set color bang, and set char bang.
Yeah. That was, I was talking about.
Yeah, it is there.
Yes.
Yeah, so that's what they call mutation. Mutation means
Yes.
change. Mutate means change. So when you talk about mutate, already there is an assumption that there is a state. Yeah, because only there is a state that you have something to change. And so we are entering a different idea now. Even though this is an idea which is very elementary, in the sense that you start learning programming language, you start you in use in usually what you do is that you start with variables and assigning values to variables and changing values of variables and so on. So it's something which goes without saying that there is a state, variables have state, and you can change those state. But in Lisp, we are entering this idea much late. Yeah. Anybody notice that difference? Hello.
Yes, sir.
And they are justifying that they are justifying the introduction of this mutation. And what is that justification?
Sir, they agree that it can create a lot of nasty bugs, but they say that it allows that greater access to the data structure. It
Yeah,
makes our data structure efficient.
that is what their justification is. So using setchar and setcadder, they give two implementations of two data structures. One is stack, one is queue. Yeah, two implementations. One implementation without using any state. Second implementation is with changing mutators. I mean, using mutators. And in the first case, there is not much difference between these two implementations. But in the second case, there is a difference. In the second case, in the queue data structure, if you want to add something to a list, add something to a queue, you have to traverse to the end of the queue. Yeah. Now, using mutators, you could actually gain some advantage in the sense that both NQ and DQ operations can be done in all one time. That's the advantage of allowing data mutators. Yeah. Now, hello, did anybody get what I'm saying?
Yes, sir.
Yeah. So, but that is an argument which is not universally accepted, because there are still programming languages. For instance, Haskell still doesn't take that view. Okay, in Haskell, if you want to write a NQ or DQ operation, there is only one way to write that. That is the first way in which we write it in our slides. Okay, because Haskell does not allow this kind of this uh, simple change of state. Okay. Um, yeah. Yeah. So then continue. Somebody continue finishing the summary. Sakar.
Yes, sir.
Yeah.
And in the end, they were talking about this complexity, running time complexity of the curator structure, means how we can perform the front in a linear in constant time, and how traversing it, this is happening on n times, and all that about this.
Okay. All right. Now, with this setcar and setcadder, can we? So we already implemented queue and stack. What is another data structure which we would like to implement? There is no light here. The light is behind me, so if I switch it on, you won't be able to see my face. That's why. Hello. I don't know what is a data structure which we can implement after list and queue. What are the kind of data structures which you have implemented? Can somebody tell me?
Sir, we can go in for a priority queue.
Yeah. So how do we do? What is a priority queue?
Sir, it is basically a sorted queue. It has first element always as the maximum or the minimum element according to which type of priority it is assigning.
Yeah. So, but to implement a priority queue, we need either a vector data structure or we need a tree data structure. Yeah.
Yes, sir.
So, uh, But there is a disadvantage in doing it. Currently, our vector data structure does not have random access. It has random access. We doesn't have random access. Yeah, because yeah, so it doesn't help us. We won't be able to perform operations in O of one of heap. Somebody remembers how we implemented heap? We need to, if we are in a position of I, we need of, I mean, if we are in a position called A of I, then we need to find out A of I by 2 and A of A of I by 2 will be the parent. So then we will need to go to that I by 2 position in O of 1 time. That is not possible in our case because we'll have to traverse the list. Yeah. So heap is not very much suitable for us using our linked list because we don't have random access. What other data structure is there? What about circular linked list? Hello.
Yes, sir. Using mutators, I think we can create a circular linked list.
Yeah. So yeah. By the way, what happened to this one? These two problems, Knight's Tour and 8 Queens. Did you do it? Did you know Knight's Tour and did anybody finish apart from Devyani?
Yes, sir.
You finished? Can you show me your code?
Yeah.
Yeah. Yeah. Okay, very good. Okay,
Are
let's.
you able to see the screen actually?
Yeah, can you share the? Can you show the explain the code?
Yeah, sure.
Uh,
Let me first run one thing. Okay, this is like if you're given a position, you will get a night tour like from that position. Like
okay.
okay, so okay, so my board is like a list of positions.
Okay. Can you first execute and show us?
Yeah. Yeah, it will take some time.
Yeah, that's not a problem. We can once we do this thing, we can do some heuristics. Then it will be faster. Did you do the heuristics already?
No, no.
Okay.
Okay. So when this
Yeah,
is
explain.
getting
Yeah.
executed, I just explain the code. So one thing is like position is a pair.
Okay.
Okay, so row of a pair will give me the, okay, row is like the row first element of that position,
Yeah.
and column is the second element of the position,
Okay.
and position of xy is same as cons of xy. It's a pair.
Okay.
And then night moves. So given a position, what all moves it can valid moves, what all moves it can make. This So knight moves of P will give me a list of valid moves from P. A knight can move. Yeah.
So let R is equal to row of P, C is equal to column of P, then list of position of R plus 2, C plus 1, R plus 1, C plus 2, and so on. Okay.
Yeah, but certain things will not be valid. That I will check in another function. Okay.
Yeah.
Okay.
Actually, what you could do is that you could take a you could just filter that list through something. You understand what I'm saying?
Okay.
Where is your checking your valid moves?
That is here in safe.
In safe, yeah. So here you are checking it, yeah. So instead of doing that checking or safe P board.
Yeah. So board is like whenever I'm running this board will collect the valid positions, like in each move.
Okay.
Okay. So whenever I'm going to add one position, I'll see if that position is safe. So, okay, safe in respect to if that position is valid, like the row and column is respect between one.
Okay. So you are doing two things simultaneously. One is that on an empty board where the knight could jump, that is a valid move.
Yes.
That is different from whether I have already visited that node in the past. So these are two different kinds of validities. Yeah.
Yeah. So both I have combined it
and combined to one place.
To one place. Yes.
Yeah. It is okay, but I would have liked it in the first sense that you have a very simple function which just checks that. For instance, if your knight is sitting on the in 1-1, then it cannot jump into anything on the 3 quadrants. It can only jump into 1 quadrant.
Yeah. Okay. I could have made this check here only.
That check you just filter it through. You make that list and then filter it through and just give it to.
Okay. Using filter.
Yeah, using filter.
Yeah. So this is the output from.
And the second one also, the safe P, again you should have you have the past moves. Okay, let's continue your logic and then we will discuss.
Okay. So this is the output. Okay.
Okay, very good.
So from 8-1
7 3 8 5. This way we cannot visualize because we have we could make it into a okay, we will change this thing. Okay, the way we can do it is let it be first. Let's hear your program. Let's see your program, and then we will present this output in a better fashion. Yeah.
Okay. Yeah. So empty board is just a empty list. Okay. And safe of given a position and a board, I am checking if that corresponding position is valid in respect to it, which is between 198, as well as it is not present in that board. This position is not already
Board
visited.
is a list of positions.
Board is a list of positions. Yes.
Yeah.
Okay. So present of P board is a function where I am checking if this position is already present or not. So it's just like traversing through each positions of the board and seeing if those two positions are equal. So pose equal is like given two positions if they are equal, if their rows and columns match.
Okay. Yeah. Actually, there is a function called memq, which is for checking if something exists in a list.
Okay, memq. Okay.
Okay, continue.
So, and this is the main function, solve KT. So solve KT, what it does is that it takes a position and a board. Yeah. So this is the initial position P. So it takes a position and I am actually inserting that position to the empty board. I'm giving it. Okay. So this is terminated if the length of the board is equal to 64. Like if it is visited all the squares.
All right.
Okay. Else, what it does is that it will call all the branches of it. Like it will call this function solve iter with this board with the knight moves of this position P.
Okay.
Okay, so this moves will be a list of positions. So I'll traverse through each of this list of positions.
Uh-huh.
Okay, whenever like I'll traverse this. So initially I'll check if it is safe. The new, so each positions in the moves will be the new position. Like I'll take each car moves with the new position,
Uh-huh.
and the rest position will be the cutter of the moves, and the new board will be the appending this board with this new position.
Okay.
And then I'm checking if the new position is safe with the existing board. If that is the case, then I'll call this all KT again with the
Yeah.
new position and new board.
One second. Let's try to understand that. First of all, can you put that let one by one below?
Yeah.
Okay. And the diff should go to the right.
Uh,
The diff,
yeah, this is like inside the slit.
yeah, it's inside the let. Yeah. I mean, ideally, it should be moved to the right a little more. Okay, that's fine.
Oh,
So
okay.
your the new position is the care of moves. The rest position is cutter of moves. So you're taking the new position. New board is up and board list of care moves. Okay, that's fine.
And then I'm checking if the new position is safe in the existing board.
Let me ask you one thing. Why did you append to the move? Why couldn't you put it in the beginning?
In the beginning,
Because if you put it in the beginning, only when you output the list of moves, then you need to be in order. Yeah, you need first position, then where the knight jumps and so on.
oh,
You understand what I'm saying?
no, okay.
So right now, what you're doing is that you are taking the board and you're appending the move to the end.
Yes, yes. Okay. What happens if yeah, that doesn't matter actually.
You could put it in the beginning because right now, even for every this thing, you are taking off one.
Yeah, so I can just use this cons operator probably.
Yeah,
Yes.
just use cons. Only thing is that in the end, you will have to reverse it. That's all.
Yeah.
Okay. All right. So new board cons of care of moves board. Okay, that's fine. If safe of new position board.
If it is not safe, then I'll call again the solve item with the cutter of the rest of the positions. If it is not safe.
Okay.
If it
Then
is safe,
let me just read it. If safe of new position board. Let result of solve getting new position new board. Solve getting new position new board.
I'll call in again the solve KT main function with the new position.
Okay, and the new board. Okay.
And I'm fetching that into the result. If that result is
If,
false,
if equal, result is equal to false. Okay.
then that means I am not able to continue with that branch. So I
Yeah.
have to call the cutter of, I mean, with the rest of
Solve
this board.
item board of rest moves.
Yeah.
Result. Okay. Solve item board of response.
If it is not, if the new position is not safe, I have to take the next position anyway. That is for this.
All right. Okay. All right. That's fine.
Yeah, that's it.
Yeah, that's it. So let's finally when we 64, just reverse that board and give it equal to length board. Just reverse that list and give it. Yeah.
Yeah.
So okay, very good. Let's try to speed it up a little.
Okay.
Give it to 1-1, yeah.
Yeah.
So one thing which we could do is that right now what your list of positions, if we go to the beginning, let's look at your new moves. Let's others, did you understand how the function works, how the program works? Let others also understand. Yeah, Saina, please take
Yeah,
some
yeah.
questions from other students. No questions. Siddharth, you understood?
Sir, I had one question. The last recursive part where we are returning if there is no new. Can you once again explain that?
Okay. Which part? This part?
Okay. So if we have no safe position.
Mm-hmm. Yeah, if we have no safe position, then we are actually going to the rest of the position. So that position is not safe. So we are going to, so this moves is like P is the position we are giving. This moves is the knight moves of P. So there can be maximum of 8 positions. So I'm checking one by one. So I'm checking whether the first position is safe. If not, then I'm taking the second position. So I'm recursively calling the solve iter function with the existing same board with the rest of the position.
Okay.
So,
And how does the main recursion is working with the help of solve it at that part?
yeah, so let's imagine, so she starts with 1 1. Now you find all the adjacent, all the possible moves from 1 1, that will be in moves. She takes the first one out of that 1 1, the neighbors of 1 1. Yeah, let's call the neighbors of 1 1 those positions where the knight can jump into. Yeah. Now you take the first possible neighbor, put it in a new position, and also check if the new position is not already visited. So ideally, here is a place where you could have made some changes. You could have, yeah. So it came actually.
Yeah.
So from 1 1, you are jumping to 3 2. Okay, and 3 2 to 5 3, 5 3 to 7 4, and so on. Okay, before we come into that, yeah, let's finish this explanation. So you take the first possible neighbor and add it to new position, and also if the new position is not already visited, and if it is a valid position, then you just add it to the already visited. So you, instead of new board, she should have called it visited. That list should have been called visited.
Ah, okay.
Yeah. No, you don't need to change now, but ideally we should call things by appropriate name. Yeah, the program logic has to be modularized in the. We should not try to cut corners. Yeah, here we have two different things to check. One is to check that we don't take -1 2 such positions into our list. That's one primary check we have to do. That should be done with the help of a filter in the beginning. That is what we call a valid position. Now, the second check is whether the position which we are considering is already visited. That's a separate check. And these two separate checks should be done differently at different places. Okay.
Yeah. Yeah.
Okay. And that's why, and it should be called visited. All right, that's fine. And so what happened in the case of Sina is that when we program something for the first time, we are not aware of all these facts. We write something and we try to make it work, and it works. Now, just like writing any good prose, programming also requires editing. You write a program once, and it requires you to go through that program and edit it and remodularize it and refactoring the code. That's called code refactoring. That is, you look at your code and you say, are the functions separated nicely? Do I have kind of awkward looking recursions or awkward looking function calls? Are the functions taking appropriate parameters? Yeah. and so on. For instance, in this case, the functions, we could actually, these two functions, solve kt and solve iter, they are kind of mutually recursive, but at the same time, maybe it is a case that we might be able to merge them into one code.
Yeah, yes, yes,
Yeah.
yes.
And is there a good reason why we should have two separate functions which are mutually recursive, or we should have one function which should be simply recursive? Yeah. So actually, if you look at this code, there is nothing which solve kt does, which is not doing, which is we can easily merge solve kt into solve kt.
And I could actually deleted this board.
Yeah, no, I'm not talking about such thing. I'm talking about we could actually get rid of that function altogether, and it is just one recursion.
Okay.
Yeah, right now we don't need to do that, but
Okay.
okay. Because you see what is Solketi doing. Solketi just checks the visited, the list of board is 64. If it is not, it is just calling solve item with a separate function. Yeah. So I could, wherever solve kt is called, I could just substitute with this solve item.
Okay.
Yeah. So for instance, wherever you call result of solve kt new position new board, I could instead check if the length of the board, the length of the new board, if it is 64. If it is 64, I return the board. Otherwise, I call solve iter again. You understand what I'm
Okay.
saying?
Okay. Like, yeah. Okay.
There is only one place that solve kt iter is used. Solve kt is used. Yeah. So there, I could actually check if the new board length is 64. The new board length is 64. I return the reverse new board. Otherwise, I return, I call solve iter board with night moves again.
Okay. Yeah. This entire part will come here.
Yeah, exactly. So it just becomes one function recursively calling itself. Yeah, so that is called a code refactoring. I'm saying that nobody gets, when you write it for the first time, nobody gets what is the ideal splitting and factoring of the code. Only just like editing is an important part of writing. You write something and then you edit it, because only when you edit it, things starts to improve. Similarly, it is an essential part of coding that you convince that your code works, and that is not enough. That is not production quality code. You now Then the job begins of looking at the code and trying to uh, eliminating the unnecessary parts, refactoring your functions, checking if the functions are taking appropriate parameters, and if the functions are nicely, very well organized, the code is placed correctly, that the functions are put in a fashion which is logically ordered, and so on. All these things comes after you get your program correctly. While you're writing the program, you will never be able to do everything. So editing your code is also is an important factor. Okay.
Okay,
All
sir.
right. That was my point. Okay. So now let's try to speed up this bit. So what I was saying is that, yeah, this is fine. Let's go to the beginning. Yeah. So here, when we are considering the night moves, we are considering first so let's call it, if I have a position P, I can consider the XY grid on that position P. So we are jumping to the first quadrant. Yeah. That is jumping to the first quadrant, the top right quadrant. That is your first positions. +2, +1. And my +1 and +2. Yeah. So that is the top right quadrant. Positions in the top right quadrant. Then comes your positions in the top left quadrant. Then comes positions in the bottom left quadrant. and then comes the positions in the bottom right quadrant. Yeah, that is how your list of moves are there.
Yeah.
Yeah.
Yes. Yes.
Okay, that is fine. Now, what I'm saying is that the improvement which I am suggesting is this: if I am sitting in a position like 1-1, okay, then there is nothing much to do. But because there is only one quadrant, only two positions are there to be considered.
Yeah.
Come down a bit. Let's see. Come down. Yeah. So the one thing is that you are actually adding all kinds of garbage positions to your moves, and then you are checking if it is safe.
Yeah.
Yeah.
Yes.
So your moves will always be of length 8. That is
Yeah.
not a big problem, but that is not a big problem. But ideally, if we could have filtered it in the beginning, then we would get smaller list. So in this case, what happens is that as you are recursively going down, every position will have a list of 8 to carry.
Yeah. True. Yes.
So ideally, if you would have filtered that list before we moved into those things, then
Mm-hmm.
we are in a deep recursive level. We would have smaller list in the recursive depth levels. You understand what I'm saying?
Yes. Yes. Yeah.
Yeah. So that is one the improvement which we could do. But anyway, that's not a big problem. That's just a memory thing. It doesn't affect our performance of our code. The performance of our code will be affected by, however, by the ordering of these moves. That's what we are going to change.
Okay.
So,
Yeah.
sir, it would affect performance, right? Because it would have to do those additional checks on the on a when we are in the recursion. It
Yeah.
will it will check all the garbage positions also.
Yeah, but it will check the no the but, yeah, I mean, wherever you check, every position will be checked exactly once, whether you check it here or whether you check it
Oh,
there.
okay.
But the number of lists which you the number of lists you carry will be, the amount of lists you carry will be different. But it's not a big overhead.
Mm-hmm.
You don't have to change it now. It's fine.
Okay.
What we have to change it, however, what we have to change is the order in which these positions will be considered, because that will have a definite impact on your backtracking. Okay, because some positions, out of these 8 positions, some positions are are fruitful, some positions are not so fruitful for finding a path. Okay, so that is called heuristics. What is the of these 8 positions, what has a better chance of completing a night tour, and what has a worse chance of completing a night tour? Okay, that's what we have to check. Now what I'm suggesting is, of these 8 positions, if a knight is sitting on a position P, okay,
Mm-hmm.
what I would like is, if it has a possibility of jumping to a position which is closer to the rim, do it first. Then then consider all the positions which are inside the. So for instance, if a position is like, let's say 2-2, okay, somebody, if a knight is sitting on 2-2, then it can actually jump to 3-1. 3-1 is closer to the rim. Yeah, 3-1 is closer to the rim. Yeah, it is sitting on 2-2, so it could jump into 3-1.
4-1, right? Okay.
It could jump into 4-1. Yeah, it could jump into 4-1, or it could jump into 4-3.
Yeah.
Yeah. Similarly, it could. Yeah, those are the only 2 positions. Now, I would like it to jump into 4-1 first, then 4-3, and the reason is this: that when I jump into the initial parts of the 4-1 position has lesser number of neighbors than the 4-3 position. You agree?
Yes.
4-1 position has lesser number of neighbors than 4-3 position. Now, why do we jump into the position which has smaller number of neighbors? The reason is because if we jump into smaller number of neighbors in the initial parts of the recursion, then for the later part of the recursion, positions with large number of neighbors will be left behind. So therefore, there is a better chance of hitting a full 64-degree tool. Anybody understand what I'm saying?
So could you repeat once?
Yeah. So what I'm saying is that imagine if my knight is sitting, Saina, let me share my screen.
Yeah,
for
I'll
it.
stop sharing this.
Everything has. And there should be knights too here. Yeah. These are all knights too. Yeah. Yeah. That's. Yeah. It is actually given here. Fewest onward moves. Yeah. It's called Wansdorf rule.
It's 11 o'clock.
Okay. So yeah. Oh, damn. Okay, so this is our chessboard. Now my point is that imagine a knight is sitting here, okay, this position. This is in our terminology, this is 2-2. Now a knight could jump here or here, okay. Now, which one we would like to consider? The order of moves we would like to consider first this position than this position. And the reason is this position has larger number of neighbors. This position has 8 neighbors. On the other hand, this position has exactly half many neighbors, 4 neighbors. So in the initial part of my recursion, if I jump in here, then all the edge positions will be consumed first, and then the inner position will be consumed. In that case, the inner position has larger number of neighbors, so it has a better chance of finishing the knight's tour than if I consider in the beginning. If I jump into the inner portions of the board, I will finish all the positions here. Then I won't have enough positions to jump for these guys. That's why, as a heuristic, this is not theoretically this does not anything. You will always finish it in exponential time. But practically, this will be a speed up. Okay. Any questions? This is a graphical representation of Wardow's rule. Each square contains an integer giving the number of moves that the knight could make from that square. In this case, the rule tells us to move to the square with the smallest integer, namely 2. Yeah. Get it? Everybody gets it? Hello? Hello?
Yes, sir.
Hello, Saina, you can share now.
Yeah.
Okay. So now how do we implement this? All we have to do is that we have to reorder those moves in the order in which the number of neighbors are the smallest.
Okay.
Yeah. So in the knight moves, you return a list. So let's try to return a list. You get that list, and first let's filter the yeah, nonsensical moves. Yeah.
Filter the valid positions, you mean, or?
Yeah. Filter the valid positions. Okay, let's quickly just see if it is coming correctly. Can you-
Yeah, one sec. Okay. Okay.
It
I
moves of
should I
one or
filter.
something.
I should write filter also, right? It's not.
It's not there.
It's, filter is not there.
Yeah, just right. Nil. Yeah. No. it's not.
The else condition for the p char of x.
Thank you.
No, something is wrong. If P of char of x is cons of char of x is filter of
Okay.
no, but those are already
No.
yeah.
This is.
Okay. All right.
Yeah.
Okay, very good. Okay, so now for every position we will get knight moves. Now what we have to do is that uh, this has to be, so now it comes 3-2 and 2-3. So but this is correctly in the order because is it correctly in the order? Yeah, this is correctly in the order because both of them have eight neighbors each, I think. Yeah. No. Three. Yeah, both of them may have like I don't know how many neighbors. So what we should do is that
Okay.
this, you should compute the night moves of each of these coordinates. Okay. That will give you the possible moves from 3, 2 as well as 2, 3. Count them and then arrange the 3, 2 and 2, 3 in that order. That's what we should do. So how can we do that?
Okay. Okay.
Yeah. So, but first tell me your idea, higher order idea. What is your higher order idea?
Okay. So first in this list should be in a order where for each positions here should have highest number of neighbors, right?
No, this list is fine. But what you don't have to change this list anywhere in this list. That is fine. Yeah.
Okay. I should change this ordering. That's what.
Yeah, that ordering we should so before we return night moves of position 1, 1, we get this list. Now what we are going to do is that we are not going to return this list immediately. Instead, what we will do is that we will compute the night moves of each of these positions.
Okay.
And then count them. And whoever comes, and then arrange these positions in the order such that the night moves are the night moves of these positions are in the increasing order. Get it? What I'm saying? So, for instance, imagine you have night moves of position 1, 1 returns 4 positions X, Y, Z, A, B, C, D. Then what we will do is that we will compute the night moves of A, night moves of B, night moves of C, night moves of D. Okay, and count them. Count how many night moves are on A, count night moves are on B, C, D, etc. Count them, and then arrange A, B, C, D in such a way that the night moves of those positions are in the increasing order.
Okay. Okay.
Yeah, that's what you should do.
Yeah, basically I have to sort based on the number of increasing order.
Number of exactly on the increasing order.
Yeah. So I put first.
Can we achieve it in some higher order fashion? Can we achieve it in some higher order fashion? I don't see any way. All possibly you can do is that you can take each of these moves, count the night moves, and count them, and put them into tuples, and then sort the tuples based on the second coordinate. That's all you could do.
Yeah.
Okay. But since we have another idea. We don't have to use some sorting algorithm. See how many possible moves our knight can have.
Maximum 8.
8.
Maximum 8. But what are the possibilities? Is it 2, 4, 6, 8? Can it be odd number? Can it be
the number of possible moves, right?
Yeah.
Yes, sir. It can be odd number.
It should be even. It can't be odd.
Yeah, I feel like it should be even. But what is the argument?
Sir, I
so
think
we can say that
1 has odd number of neighbors.
Which give me a position.
Even on the Wikipedia page you showed, there was a position with 3 written on it.
Sir, 2, 1. For example, 2, 1. It has three neighbors.
Yeah, it has 3 neighbors. Yes.
3 neighbors. Okay, so then we can't do much. But what you could possibly do is that we could have You can have a simple insertion sort.
Okay.
Yeah. So basically what you do is that, yeah, let's, should we, yeah. So first, yeah, so we have this list, night moves of P. Before we return that list, this night moves is P is fine. Let's call it moves of P.
Okay, and the new function, right? Or the new function, right?
Yeah, moves of P. Yeah, so this function, what should it do? It should count for each P in the night moves of P. It should count the length of that list. And then it should create a tuple, a pair. Yeah, exactly. So we can have a map which maps.
Each position it takes and gets the length, right?
Yeah, length.
Length of the night moves of that position.
Yeah.
And it is mapped to the night moves of P.
Yeah. Lambda position length of night moves and position. So make it cons of length of night moves. Cons of post comma length of night moves.
Okay. No, I didn't get it. Make it.
Yeah,
Okay, I want a
concat map, concatenation map.
pose and length of.
Yeah, post and length of night moves. But it could, instead of a map, it should be a concat map. It should be concatenation. It should be a list of those maps. List of. But these are not. But there is something wrong. There is no concat there. That's why. So basically, what I'm saying is that you get the night moves of P, and then you create a tuple which contains the position as well as the length.
Yeah. Yes. So a concat is required because it is taking each position and giving you a pair, right?
Yeah, it gives you a pair, but now what do you do with the pair? You have a number of pairs. Yeah. No. That is fine. That is fine. This is fine. This is fine. Yeah. This is fine. That is not needed.
Okay.
Somewhere something is wrong.
Okay, I have extra 10 seconds.
Before cons, you have two brackets, just one bracket on cons.
Yeah, this is extra bracket.
Yeah.
Right?
Yeah.
No, lambda should be closed before night moves.
Okay. Yeah. Yes. Thank you.
Okay, that's fair enough. So what I was saying is that if we had only three, let's say four positions, like only four possibilities, 2, 4, 6, 8 and so on, then we could have a bucket sort or a radix sort, which is because basically all we have to do is that we have to sort into 4 buckets or 4 radixes. But since we have 8, maybe it might be easier to do an insertion sort. Yeah. So now we get these tuples, and then just get it to a let and then just sort it based on the second component. So let's do one thing, Saina.
Yeah.
I mean, others have time. So it's already 11:18. You have class. When is your class now? Hello.
So we don't have class at 11:30.
Okay, so then let's finish. Yeah. Okay, let's finish this. Okay, so now let's get it into one an insertion sort. So let's put let and list. Now here itself within the moves we can sort. Yeah, you just say let sequence or k-seq or something.
No, what do you want exactly? See. Okay.
Yeah, just put some name, move seek or something. MOC. Yeah. Move seek. And then this one.
Okay.
Yeah. So now what we should do is that we should sort this list based on the second argument. So let's do a iterative sort.
Okay.
So it's like I sort.
Should I define? Okay.
No, we can define it outside.
Yeah.
Or we can define it here. That's not a problem. No, you can't define within a let. You have to either define it outside or define isort. Then 2 sequences, x's and y's. Let's do it iteratively. Ys.
Okay.
And so you take the first, you take from x's and you put it into ys.
Okay. Okay. So if null of x is right.
Yeah.
X is give ys.
Yes.
Else. So each time when you are putting it, you have to put in the correct position in ys.
Yeah.
Okay.
So you have another function like insertions, insert or something.
Define insert this value x into
Some
a
x's.
list ys or something. Okay. That is.
Yeah.
Yeah. So if so you have to insert it in increasing order.
Yeah. You have to insert it in increasing order.
So till you reach the end, you are saying your x is still greater than the last element.
Yeah.
Then you have to.
So if it is just if it is null, then you return
List x and nil.
Yeah.
Right.
Yeah.
Else, if I have to check if that if x is less than r of zs,
Yeah.
you have to consect with zs. Else,
We have to change that less than to another function.
zs
Yeah.
with the
We have to change that less than because we are sorting based on pairs.
sorry sir, okay.
So that less than has to be some other function is my point. Yeah. Just call it like less some other function, less than or some yeah, second less than. Yeah, second less than. Yeah, that's fine.
Yeah.
Second,
Maybe here only we can see if the okay, we should not complicate. Thickness of 6 and y will be true if r of color of x is right.
yes. It's not care of
Color of
the way we do it. It is
okay, this is just position, so it's
it's
color.
just color, yeah.
Yeah, it should be less than or equal to.
No, less than is fine. Why should be? Yeah. So you finish this I sort.
Okay, if okay, yes. Else I'm checking if
X's is null, then yes. Otherwise, you insert a char of x's into yes.
insert, yeah. Insert.
Char of x's into yes, and you call I sort with color of x's and this one.
Yes. But
Yeah, you in the beginning you have to also insert call I sort again.
okay. I sort with
Color of x's
x's and new this will be
yes.
right.
Yeah.
Yeah.
Okay, so that's fine, and then you just call insert I sort with mouse. I sort with this move seek an empty list.
Okay, let this move seek is this. So I should call this I sort of this move. Seek with the empty list.
Yeah.
Okay. That should be fine.
Something is wrong. Second less is
Because this will be um,
Contract violation, expected M pair, given empty list.
Sir, when y is empty, then we are trying to take the cutter of y. That's why it's raising an error.
So why is it the case that y is empty?
So we start with y is empty, right?
Yeah, but we are checking if ZS is null, and then going into second list. No?
So we are taking the list of X and L. It should be cons of X and L.
Yeah, true. Yeah.
Yeah, or just a list of X. Yeah, that should have been also. Yeah. Let's see if that works.
Yeah. Yeah, 468.
Okay, that works fine. Now all we have to do is that we just have to strip off those this one. So let's try another map.
Okay. Here only we are going to do it? Or?
Yeah, let's try strip off those first. Let's put a map.
So here, map, we are taking each. Okay, why? Each position. Taking and
yeah.
I want only the care of each position, right? Yeah.
Okay. So now let's go down and replace the night moves with just moves.
Yeah, maybe I can okay, remove this condition also, right? Okay.
Yeah.
Or should I can remove this.
Yeah, and you'll move the hand also.
Yeah. And instead of night moves, just moves. Yeah. Is it right? It came so quickly. Yeah, it came.
Wow. Now that's speed up.
Like it was so fast. Yeah.
All right.
Yeah.
All right. So please, others also please do this night stool and this one. And so for Wednesday, let me share my screen.
Yeah, sure.
So for Wednesday, you do lecture 13, trees, graphs, and search. I think you have already done that and graph search. I mean, these are again like breadth first search, depth first search, such kind of things. You already know these things. So maybe you can do both trees, graphs, and trace and graphs. Yeah, there is only one here. Yeah. Trees, graphs, and search. No, it's the environmental model. Okay, lecture 13, environmental model. Okay. So Wednesday you do lecture 13, environmental model. And once we do object-oriented programming, I would also like to brush up on C++ and all the aspects of C++ coding. Okay. Okay. Anyway, let's talk on Wednesday. So lecture 13. And please do these two, Knight's Tour and 8 Queens. Okay. Hello.
Yes, sir.
Thanks everybody. Yeah. See you. See you on
Thank you,
Wednesday.
sir.
Yeah, bye.
Thank you, sir.